Okay, so I'll start the webinar now. So welcome to the webinar of today. So it's the second webinar of the series, and the topic is applications of piezoelectric materials, and I'll be giving the talk. And you can see the rest of the webinars here. So if you see some interesting topics, please don't hesitate to register for the upcoming webinars. So I'll change to the presentation now, if you hang on for a moment. So, as I said before, there's been some indications of sound problems. So please, if you cannot hear what I'm saying, please just send a chat message. So I'll also put it on a chat, just a minute. Okay, so I will start now, assuming that everybody can hear the sound. So the topic of today is applications of piezoelectric ceramics. Yeah. Yes. So I'm just checking with my colleague if the sound is going through. So the topic of today is applications of piezoelectric ceramics, and I will just get a laser pointer. So here you have an overview of the topics of today. So after the introduction, I will go on with a lot of different applications. I can tell you that all in all, we have more than 20 applications that I would like to show you today, but it will be a very short overview. It's just really to give everybody a sense of what can be done with piezoelectric materials. So it's not even an exhaustive overview. It's just 20 applications that are giving good examples of the possibilities of using the piezoelectric materials. Okay, so I have confirmation now from certain participants that you can hear me, so I'll just go on. Okay, so first I'll give an overview based on the type of effect. Those of you who attended the first webinar will know about the direct piezoelectric effect and the converse. So first the direct effect, where we convert mechanical energy into electrical energy. So one simple example is the ignition unit, where you ignite, for example, a flow of gas with a spark, which the spark being generated by the stress converted into an electric spark. Another similar application with the direct effect is pressure sensors, where you have a pressure and you convert that to an electrical signal. And I'll also show an example of a hydrophone, which is basically an underwater microphone. So moving now to the converse effect. One example that I showed last time was the buzzer, so a kind of loudspeaker where you convert the electrical signal into some vibration. I can also mention ultrasonic cleaning and other examples here on the list. You will see some examples in a moment. And finally, here on this slide, I'll show you that quite a few applications use both effects. So here, for example, the medical imaging, you use both the converse effect to generate a sound signal, and then you use the direct effect to convert the sound signal into an electrical signal. And basically the similar principle is used for underwater acoustics or non-destructive testing, as you'll see a little later. Okay, let me move on. Just by saying that you see that the piezoelectric effect can be a link between the electrical and the mechanical world. So another overview is this one. It's a little less colorful, but it's giving one extra detail that some applications are resonant applications and some are non-resonant. So looking here, you can see that in the resonant applications, you have, for example, the bulk acoustic waves and the surface acoustic waves, and also a lot of ultrasonic applications use the high conversion efficiency obtained at resonance. And there are also some resonance sensors where you actually measure the shift of resonance frequency. And among the non-resonant applications are the actuators, for example, and some of the piezoelectric motors, and also especially the positioning devices. Yes, and in the other end, using the direct effect, you have a lot of sensors that are non-resonant, like force and torque and acceleration sensors. So to begin with, you have the simple application that I mentioned before, the piezo lighter, where you generate a spark to ignite the gas. This is at a rather low frequency, and whenever relevant, I put the operating frequency in the top of the screen. And you can see here another example is the hydrophones, and these hydrophones are omnidirectional and therefore the spherical shape. Also in the sort of low frequency range, you can see some examples here of ultrasonic motors, like these small motors inside a camera lens. So next example I'll give is the application of vibration sensors. You see here an accelerometer, basically a rather simple design, where you see the piezoelectric ceramics shown here as 3 red discs, and they are just stacked on top of each other. And on top of those, you have a seismic mass, which is just some weight that will give a higher output because of the higher stress value when you expose it to some vibration. So the seismic mass is kept in place by this pre-stress rod. And you can use this with only one ring or with several rings, and generally it depends on how sensitive the material is. For material with low sensitivity, for example, at high temperature, you would use several rings rather than just one. And such a sensor may look like this, with some tight housing around it. It's interesting to think about the frequency also for the accelerometer application. You generally use them in the linear range, so you really want a flat response depending on the frequency, so that you can be sure that in the designated frequency range you get a quite linear behavior. And then when you approach the resonance frequency, you are basically outside the usable frequency range of the accelerometer. Another plot is shown here where you see that typically the frequency range that you can use is maybe up to 30% of the resonance frequency. In cases where there is a high transverse sensitivity, you actually should be careful that even the transverse resonance frequency may may actually limit your usable frequency range. I have some examples here of accelerometers. So these are designed by the company Brüel & Kjær. And in this case, it's not pure compression. We use the shear mode. So a famous design of these shear mode accelerometers is the so-called delta shear, where you have 1, 2, 3 plates, shear plates, which are here marked in red. And they are attached to a center rod, which is triangular. And outside these 3 shear plates, we have the manufacturer has attached some heavy plates of metal. So it's actually seismic masses, one for each of these plates, meaning that when the accelerometer is shaken up and down, you actually get an electrical signal, and depending on the direction of the vibration or acceleration, you get different signals from these 3 plates, meaning that you have a true triaxial measurement. Here you see some other examples using the shear mode. Also here you have 2 shear plates, and in this case it's one shear tube with the seismic mass also being tubular and fitted around it. So let's just see. Now I move to the next application. So you just see here. Okay, so and now moving up in frequency, we come to the example of ultrasonic cleaning and machining. So generally the frequency is rather a bit higher here. It's a few kilohertz up to even 500 kilohertz. So in this case, there is an ultrasonic bath, and you have some discs of piezoceramic material attached to the outside of this steel tank, and using ultrasound you can actually generate high amplitude ultrasonic waves in the liquid inside the tank. So this is very efficient for ultrasonic cleaning, which is well known in the laboratories, and even for cleaning glassware, or for cleaning glasses at in the optic shop. Okay, so another example here, sort of in the same corner, is the ultrasonic machining, where you can use ultrasonic welding. If you want to join 2 pieces of plastic or 2 pieces of metal, it's a very efficient way of getting a very quick joining just by rubbing 2 pieces of material together, and then you'll get a softening or even local melting just in the friction zone. So an example where this is used is for the attachment of these plastic mounting devices to the bumper of a car. So these inserts are actually for holding distance sensors, acoustic distance sensors for controlling whether you hit something with the car. And these fixtures are actually attached to the bumper, just using this ultrasonic welding for a very short time, just less than a second. I have a third example on this slide, and this is for ultrasonic cutting and grinding. So, the point is, for very hard materials, you can actually, instead of using just a hard metal for cutting or drilling, you can actually use an abrasive slurry, meaning a suspension of hard abrasive particles. And then the movement is coming from a transducer working, for example, at 20 kilohertz. And when this tool is vibrating up and down, you will actually machine material off the workpiece. So a very efficient way for for hard materials. The next example I've chosen is sonochemistry and chemical extraction and other industrial processing. So beginning with chemical reactions, these are 5 examples of chemical reactions that can be performed basically without any ultrasound. But the point is that if you use ultrasound in a smart way, you can really make them much more efficient. So if you're a chemist, maybe you'll recognize some of these reactions, but this is not that important. Just look at some examples. With 18 hours of reaction time, you may get 88% without any ultrasound, but then when you apply ultrasound at the right conditions, just in 1.5 hours, you can get a higher reaction completion, so you can get a 95% reaction just in a fraction of the time. And you see some other convincing cases here. For example, for oxidation here, maybe you get almost the same conversion efficiency, but in 1/4 of the time. And this is how it may look. In practice, you have a reaction mixture down here. Then you attach the ultrasonic horn, and you see the transducer is up here, and the vibration is transferred through this mechanical arrangement, and then the sound energy is really transmitted into the reaction container here. And of course, it's important that the whole apparatus is fixed at a node point, meaning a point where there's zero displacement. Otherwise, it'll be very difficult to hold the whole transducer assembly. I have a further figure here showing one example where you see again the ultrasonic energy transmitted down here, and inside the bubble you can actually have some reactions going on. Like in this case, it's the dissociation of water molecules, so that you actually get a free proton here, which is ready to react with the copper. So you transfer a lot of acoustic energy, which will really enhance the operation. Okay, moving on, there are some other examples of using ultrasonic energy to enhance certain processes. So, for example, if you want to dry or dehydrate some material, you can combine conventional heating with ultrasound or other types of heating, like microwave heating and even vacuum drying. The point is, if you combine those with ultrasound, you will have a much more efficient drying or dehydration. The next example is for extraction from various materials. For example, here from some organic materials like pomegranate or mango peels, olive leaves or peanut seeds. You can extract certain substances from those with the help of ultrasonic energy. And yet another example I have here is extraction of minerals. So this case is actually some intermetallic compound of aluminium and zirconium, where you have a much better extraction using the effect of ultrasound, where you can, for example, break large agglomerates into smaller agglomerates and get a higher active surface. These are just some figures from the paper showing some study of how the mechanism of extraction can be optimized. The final examples are for heat transfer enhancement in liquids and for the recovery of oil. Now moving to something very different. It's the underwater acoustics, and in the first example, I show how it can be used for fish finding. So here you see a fishing vessel, and on the bridge, it may look like this with a lot of computer screens, and on some of the screens you can actually see what is the image generated by the fish finder, by the acoustic fish finder. So you can actually see basically the density of a school of fish, and also get a size distribution of the fish down there. And looking at another screen, you can really see how large the school of fish is, and also in which direction it is located and moving, so that you can quickly move in on it and start catching the fish by throwing out the net. A transducer for this may look like this, so it's completely encapsulated and can be mounted on the hull of the ship. Next example of underwater acoustics is for mapping and searching. So first, a case where the objective is to map a canal with a rather simple cross section, but you actually want to map out the depth and make sure that there are no objects in the way. So here you see a number of transducers that are mounted on a boom like this, and with such a measurement you can actually have quite a detailed mapping of what is down there. You see in this case it's down to 6 meters, and this example is actually from Venice, where you can even see some small boat or barge down at the bottom at around 6 meters of depth. Another example is at a higher depth, where you actually see a shipwreck on the bottom of the sea. And finally, this is used a lot for so-called bathymetry. This is the mapping of the bottom of the sea, basically, and we can go down to quite a high depth using ultrasound. I have one example here of a very large transducer array. You see there are 3 persons working on mounting this at the bottom of the ship hull, and this is actually quite large elements, and the resonance frequency may be as low as 12 kilohertz, and with such a low frequency you can actually have a very large distance where you can map the water, the bottom of the sea. So it could be like in the case of the Tonga Trench or the Philippine Trench, where it's down to 11 kilometers of depth. This can actually be mapped with this kind of transducer. Final example of underwater acoustics is actually for positioning. So you can think of something similar to a GPS, but something which is working underwater. So here you have a transponder at the bottom of the sea. So basically something receiving an ultrasonic signal and sending it back. And then if you are in a ship with the right type of transducer, you can actually send signals down to this transponder and get an idea of where you are in comparison or relative to the transponder. So you can see some different designs of the active device. This is almost spherical and gives a very high angle of acoustic signal, and it could also be a more narrow angle, like in this case. And this is what is really mounted on the hull of the ship. So it should be mounted like this with the screws, and then when it's active, you can actually lower it down into the water to get to move free of the ship to get a good signal. Another case of application is for an oil rig like this, where you may need a very high precision. So here you have 4 transponders, and you can actually get the distance and the bearing relative to all 4 transponders at once, and you'll get some kind of screen view like this, where you can see the direction and the distance to all the transponders that are within range. New application, flow meters. So first I'll show the most common one, which is the time of flight flow meter. Here, a sound signal is transmitted from transducer A to transducer B, and also signals sent from transducer B to A. So if the time of flight from A to B is the same as from B to A, it means that the liquid in the pipe here is actually not moving. But once you can detect a difference in transmission time, you know that the liquid is moving, and from the difference in between the 2 time values, you can actually deduct the velocity of flow. So you really get a flow measurement with this relatively simple measurement. Of course, you need to take into account also the angle of transmission relative to the direction of flow. Another principle is shown over here. This is the Doppler flow meter, where you actually have a transducer, just one transducer, and then you are transmitting a wave, and you are listening for the received signal. And if there is a frequency shift between the transmitted and the received wave, this is actually a Doppler shift. So that will actually give you a measure of the velocity of the flow. But for this, you need some kind of reflectors inside the liquid. So it could be bubbles. It could also be some particles like sand particles in a river or something. Third type of flow meter that I'll show is the vortex flow meter, which is mainly used for gases. And here you actually generate some vortex in the flow, and depending on the sound generated by this turbulence, you can actually also calculate the flow velocity. Yeah, and as you see in the comment, it may be very important to have a very precise measurement of the flow, because sometimes it's very valuable liquids that are being pumped or sent through the pipes. Next application I'll show is ultrasonic Doppler devices for the medical field. So one example is for measuring the heart rate. This is one case of a Doppler measurement device for fetal monitoring. So you can actually detect the heartbeat of the fetus of a pregnant woman. And there are other cases of other probes. Again, you see you can actually get the pulse rate here. So let's say the heart rate of 150. So probably a fetus. And other designs here where you have a different design, and you may do a lot of statistics, and this is very good for also for monitoring of patients. These are some examples of vascular probes that can be inserted into, for example, a blood vein, and do measurements inside the veins. And here you see also a case of flow measurement, possibly for patients where there's less, let's say, circulation of the blood for some reason. These are examples of transcranial probes where you can actually measure through the skull, and invasive probes that can also be inserted inside the body, possibly during operations. A further case of blood flow monitoring is an advanced one, the vector flow imaging, typically operating between 2 and 5 megahertz. So in this case, a multi-element array transducer is used. And here the example is with 192 elements working at 4.1 megahertz. And here we are looking at an artery close to the heart, a carotid artery. And exactly we are looking at a bifurcation where the blood flow is actually disturbed for some reason. So here you see the image is generated. So the bifurcation is here. You actually see a very nice flow profile showing the velocity as a color code, and you also see the directions. And what you should notice here is that up here you actually have some turbulence. You can see some of the arrows going in the other direction. So this is what we would call less optimal flow, of course. And this is actually, in this case, it's a simulation, and over here it's a measurement of the real case, where you actually see in the MR scanner, a section of the artery, and again you see the real measurement of the blood flow. This is the reference for this study. Yeah, and further case of the measurement which is done in vivo. So the next example I'll show is for the ultrasonic imaging. I mentioned this example in the lecture, in the first webinar. So this is a standard baby scanning or ultrasonic imaging of a fetus, where the frequency may be typically a couple of megahertz, but ultrasonic imaging can be used even down to a few hundreds of kilohertz, or maybe 100 kilohertz, depending on how deep you need to go in the body and how high resolution you need. So for very high resolution, if you need to distinguish small details, you actually need to go to a very high frequency. Another example is here, and this is using a very advanced setup where it's a 3D measurement which is performed by a large two-dimensional array, and actually you can basically get a movie with showing the movement in real time of the fetus. Now I come to the other important part of medical ultrasound, which is therapeutic ultrasound. So not just for seeing things and for diagnosing, but for actually treatment of different diseases or conditions. So generally the intensity is much higher than for diagnostic ultrasound. It may be 10,000 times as high as for diagnosis. And an important case here is when you use focused ultrasound for treating some medical conditions. I have more details on that on the next slide, but it could be for destruction of tissue or for neurological stimulation. Other biomedical applications are listed here. It could be for drug delivery. For example, if you want to administer some drugs directly to the brain, normally you'd have the problem with the blood-brain barrier, but you can, with ultrasound, you can actually open the blood-brain barrier if you do it in the right kind of stimulation. There's also the treatment of vascular occlusions, and you can also use it for wound healing in some cases, and also for cosmetic treatment. So this is a case of the well-known example of the lithotripta, where you are blasting kidney stones. This has been known for many years, and this is an example of a treatment of a vascular occlusion, where you can actually transmit the sound, the acoustic energy through this very thin tube here. Okay, so going more into details with the focused therapeutic ultrasound, I have looked up in the Focused Ultrasound Foundation, the FUSF. They have listed rather recently no less than 152 different clinical indications that have been looked into using the treatment with ultrasound. So this is a very quickly expanding field. In 2018, it was only 53. So already now, 34 of these treatments of some clinical conditions have approval in one or more countries. So I mentioned the lithotripta already, but a very interesting field is the destruction of tissue. This can be by thermal ablation, or it could also be by histotripsy or microvascular disruption. So for example, cancer therapy, where you want to kill cancer cells, basically. This had been used already for treatment of prostate cancer, bone cancer, and so on, as you see here. Ultrasound can also be used to treat uterine fibroids and also breast fibroadenoma. So, some conditions that may be, treated possibly by surgery, but could be treated in a much less invasive way by focused ultrasound. We also have examples of thyroid nodules or glaucoma in the eye. Among the neurological diseases that have been looked into is essential tremor, where the patient is shaking, for example, shaking of hands. Some tremor is also seen in some cases of Parkinson's disease, and both have been treated quite successfully with focused ultrasound. Another example is neuropathic pain, where you have pain related actually to some limbs that have undergone surgery. So even pain related to amputated leg or arm. It has also been used to treat obsessive compulsive disorder and depression. So I'll give some examples in the next. I'll just point out that you may have heard the term HIFU, high intensity focused ultrasound, which is quite popular in this field. So I look a little more into the case of prostate cancer. So according to one of the companies making equipment for this, at some point there were 39 million patients just in the industrialized countries. I think the number is higher now. They can in principle be treated with a less than 3 hours session and with a very high success rate and without being hospitalized. So this is how it may look. You have a focused ultrasonic transducer here. So it's really shaped as a lens so that you can focus the energy in a certain area of the prostate gland where you want to ablate the tissue. So in this case, it's focused ultrasound from the outside. There's another design here from another company where it's actually a linear array of transducers that are transmitting ultrasonic energy into the prostate gland like this. And in this case, the the ultrasonic energy is also supplemented by cooling, because you actually need to protect the tissue around. So it's actually water cooling here performed through the anus in order to prevent the same tissue. Yet another example of focused ultrasound, therapeutic ultrasound, is the movement of kidney stones. I'll not go too much into details, but you see different sizes of kidney stones that have been actually moved around just using ultrasound, focused ultrasound. And yeah, some results from this study where it was shown that it was easier to move smaller than larger stones, but even kidney stones up to even 10 millimeters of size could be moved several millimeters. And the point or the objective was to move them close to the urine canal, so that you could actually get them out without surgery. These are some images showing a real study on a in vivo on a patient. So now moving to a very different case, acoustic wave filters, and this is the application that I know of using the highest frequencies. So the highest frequencies I've heard of is 16 gigahertz, showing that the piezoelectric effect is actually an effect which is extremely useful for high frequencies. In these cases, the manufacturers tend to use single crystals. So more traditionally, it's been made of quartz in special cuts, meaning special directions compared to the crystallographic axis. And the frequencies may be even down to 1 kilohertz and as high as 300 megahertz. More recently, in the last couple of decades, surface acoustic waves filters have been developed, and these may be up to, for example, 3 gigahertz, using materials such as lithium niobate or lithium tantalate. And generally, this will use an interdigital transducer with an electrode pattern with the single lines being in this interdigital pattern. Even more recently, bulk acoustic wave filters have been generated, and this may be up to 16 gigahertz, as I mentioned before. And different designs include the film bulk acoustic resonator and the air gap resonator and the solid mounted resonator. So a device may look like this. So it can just be mounted on a PCB, and this is an example of how these interdigital electrodes may look. So you have two reference signals here, and then you have the signals, the real signal paths shown here. So the idea is that if this is really optimized for a specific frequency, you can filter out undesired frequencies because they will not be transmitted effectively through this filter. This is one example of how this bulk acoustic wave filter may look in the case of this solid mounted resonator. So you see that there are 3 layers here with different acoustic impedances, and then the objective here is to really get the right thicknesses so that you can have a good transmission at very specific frequencies and filtering out the undesired frequencies. Here you see some plot of performance versus frequency. So when you go up to very high frequencies, you generally need to move away from the SAW devices and up into up to the bulk acoustic wave filters. You see one example here is local area networks like this, working at 5.5 gigahertz. So the final application I'll touch upon is energy harvesting. I've noted that it's popular. It's received a lot of interest. Maybe I would say that commercially it will not be as important as many of the applications I've shown so far, but it's actually still a very interesting application for development and for some future applications. So you see some reasons for developing energy harvesting here. You can actually replace batteries or power cables, which will give you a lot of freedom and maybe make you able to apply a lot more sensors than you would be able to in the case where it was necessary to either change batteries or to make wiring to a large number of sensors, which would not be feasible. So some examples that are actually in use are smart metering for energy and tire pressure monitoring. So this is like a case where energy harvesting is used for these energy meters, and this is a case of the tire pressure monitors. So just to give an overview, such energy harvesters could work in compression or flexion, and they can work at different frequencies. So either below resonance in the quasi-static case, or even dynamic below resonance, or for the highest efficiency, you could actually hit a resonance where you can get a higher energy conversion. So I have some examples showing the some energy harvesters we have worked on, which are working in flexion at low stress. So some general considerations of this case, where it's basically a vibration sensor where you want to have as high an output signal as possible, and then you can compare the outside resonance and the resonance case, where at resonance you actually get a much higher displacement due to the quality factor of the resonator, of the oscillator. I would like to just mention that there are different figures of merit, and it's well known in the field that the figure of merit for energy harvesting is the D coefficient times the G coefficient, but sometimes this is used in an incorrect way, because what people generally find in tables of material properties is sometimes the D33 and the G33, but it's very important to notice that this is valid in the case of pure compression. So if it's a bender, like I showed before, a bimorph or a flexion energy harvesting device, you should actually use D31 and G31, and you may not actually see an optimum for these two parameters for the same materials as when you look at the D33 and the G33. So just to show some examples of some of our materials, and especially if you want to optimize this D33 times G33, you should actually go for a porous PCT material, where you get a very high figure of merit. But if you think that this would be useful for flexion, you can actually compare the numbers and see that here you actually have a much lower figure of merit in the case of the flexion figure of merit. Okay, so as I mentioned, it looks a little different when you are at resonance. Then as long as you can get a fairly high Q and a fairly high coupling coefficient, the figure of merit can actually be reduced to just the quality factor of the resonator. Okay, I have now reached the conclusion. So as you've seen, piezoelectricity can be used for very large number of applications. We've seen some 20 applications here, but there are more than that even. When you want to have a link between mechanical and electrical energy. We've seen examples of the direct effect and also of the converse effect, and of course even cases where you use the two in combination. So you need to choose the best material for a given application, and that really depends on the operating conditions. And I haven't given a lot of cases of, for example, high temperature applications, but this could be for accelerometers where you may need to operate at above 500 degrees, so then you need to find a material that will withstand such high temperatures. So generally you need to find the right trade-off between different properties. In the end here, I showed examples of the concept of a figure of merit that may help you to choose the best material if you know that for a specific application. Okay, this is the end of the talk. So now, if there are any questions, you may put them on the Q&A, or either this or on the chat. It's up to you. So I'll just wait if there are any questions to these very different applications. I hope you've had some impression of some of the very different uses of the materials. I'll just wait a little. So let me just see. I think as far as I can see, there are no questions for this. So I think we can end the session, and I will before ending, I will just stop sharing here, and maybe go back to the overview of the webinars that you see now. So please think of the upcoming 4 webinars. I can recommend all of them. And the next one is done by Thomas Kelly from Precision Acoustics. And here you'll get very good insight into the fundamentals of how to design ultrasonic transducers. So hoping to see some of you on the next webinar, which is on the 9th of November. Okay, thank you to all of you for attending. Bye.